Okay, a couple questions were asked about the October 12th, October 15th practice problems. In Canvas, in the link, they're listed as October 12th practice problems, and then the file is actually called October 15th. That's why both numbers are used. But anyway, so the question is, are these pairs of molecules the same, but they're not meso? Are they the same meso compound? Are they enantiomers or are they diastereomers? Couple things, there's two problems, A and B, that I will explain here. Now, if your choices are those four, same meso, same not meso, enantiomers and diastereomers, whenever you have a single chiral carbon, you can eliminate these two possibilities. You can eliminate that they are diastereomers because diastereomers require at least two chiral centers. And you can also eliminate the fact that this is a meso compound because it also requires two chiral centers. So our choice is that these two molecules are the same, but they aren't meso, or they're enantiomers. And so that's our two choices with this pair. So we have a couple of ways to do this problem. For this problem, we could determine, the first way to do this would be to determine whether each one is R or S. And if they're the same, if they have the same configuration, they're same, not meso. If they have opposite configurations, then they're enantiomers. The other way we can do this is we could try and rotate the molecules into each other and see, do we get a mirror image? Do we line up only two groups but not all four? Can we line up all four groups? So that's another way of doing this. And then we can also do this a third way by using our group switching and see how many switches does it take to get from the left to the right. So I'm going to show you all three of these because all three of them can be useful depending on the particular problem. So let's deal with R and S first. So what's the configuration of these two molecules? And if you want to check and see if they are R and S, you can go ahead and stop the video and do it and then come back and see if you were correct. So looking at this for R and S, I've got a chlorine, an OH, a Br, and a carbon. Carbon is clearly number 4, bromine is number 1, chlorine is number 2, and OH is number 3. So in this case, the number 4 group is away from me, and going from 1 to 2 to 3 then is clockwise. So this molecule on the left is R. Okay, same thing over here. The numbers are going to be the same. Number 1, number 2, and number 3 for the oxygen. In this case, I've got to put the 4th group away from me. I could just switch 4 and 3 if I want to use the group switching technique. And then I'll just go ahead and switch 1 and 2. So I've switched 2 groups twice. That means whatever I determine now is going to tell me the original problem's answer. So in essence, I've rotated the molecule. Once 4 is away from me on the dashed wedge, and that's the goal of group switching, is to put number 4 on the dashed wedge. Then going now from number 1 to number 2 to number 3 is also clockwise. So that means that both of these molecules have the same configuration, R. And so that makes them the same, and they're not meso. To differentiate between other problems where the molecule is the same meso molecule. Okay. For this molecule on the right, we could, if I put the original numbers back, the 4, the 1, the 2, and the 3, If I wanted to, I could have done this. I could have said, let me grab number 1, rotate 4 into 3, 3 into 2, 2 into 4. Again, the molecule would go back into its original orientation. Number 1 didn't move because I grabbed it. 4 went behind. 3 came forward. 2 went over. And so now 4 is away from me. And again, going from 1 to 2 to 3 is clockwise. So I get the same answer, R. Okay, so that's the first way we can do this problem, is we can determine the R and the S. Okay. Another way to do this problem is to see if I can somehow convert or overlay these two molecules. So here's another way to do this. I've got the OH, and this does not require I use R and S. This is just a visual method to compare the two molecules. Okay, so here's the two molecules again. Now what I need to do is to try and rotate the methyl group to the back. I just have to line up groups. So the way to do this might be to say, okay, let's see if I can orient these groups together. So maybe for the molecule on the left, I'll start out by grabbing the chlorine and now rotating the methyl group to the front, the OH over here, and the bromine there. So if I do that, here's what my molecule will look like. Again, I didn't change the chlorine. I put the bromine now in the back. My OH comes, or my CH3 came forward. And then my OH group goes here. So now I've lined up the two CH3s in the same position. Okay, now can I rotate this molecule and line up the Cl, the Br, and the OH? Okay, let me take this molecule now, grab the CH3, rotate the OH to the back, the bromine to the front, the chlorine up front here, and what's that going to make? Now I've got my CH3 here. My bromine comes to the top. My chlorine goes where the OH goes to the OH position. So that's now chlorine, and my OH position goes to the back. Now if we compare these two molecules, this is now the rotated left molecule to the original right. All the groups line up. And so those two molecules are the same, and they're not meso. So we could try and transform one molecule into another by doing the rotation. You might say, well, what would happen if these molecules were different? Okay, or they were enantiomers. Let me rewrite these two molecules again. So let me take the Br, OH, Cl, and CH3. So this is the original left or the original right-handed molecule. And let me take this molecule right here, this one that I had done a transformation on. So chlorine, bromine, OH, and CH3. So chlorine. So here's my CH3 was here. Then my chlorine was here. My Br was here, and my OH was here. And so if we go back and look at that, that's this molecule. Now let's just imagine, for the sake of argument, I know I can rotate these molecules and make them the same, but let's say these were enantiomers. So if they were enantiomers, what would happen is that the let me just go back and let me interchange the BR and the OH. So let me put the BR here and the OH there. Okay. Now these, since I switched those, they should be enantiomers, but here's what happened. Here's the other possibility. So I've lined up these two methyl groups. Now let me go ahead and grab this methyl group and rotate then the BR to the top, the chlorine to the bottom, and the OH there. If these two were enantiomers, what would happen is I still have the CH3 lined up. Now the bromines are lined up, but notice that if the chlorine comes down here and the OH comes here, I can't line up the Cl and the OH. So I can only line up two groups and not all four. If that's the case, then in a one carbon case, this would be enantiomers, and those chiral centers would be mirror images. Okay. So your choice is either when you try and align the two groups up by rotation, you're either going to be able to align two groups, and if two groups aren't aligned, those chiral centers are mirror images. In this case, that makes those two molecules enantiomers. Or on the other hand, if they are the same configuration, then you'll be able to line up all four of the groups. So if the chiral centers have the same configuration, then you'll be able to overlap all four. If they don't, you'll only be able to overlap two. So that's the way that we would rotate, trying to rotate the left molecule into the right molecule in order to superimpose them. Now, the group switching is another way to approach this problem. And so with the group switching, what we would do is we would, again, I'm going to go ahead and just rewrite these. The original problem, which was what's the relationship between these two molecules? And that was, so bromine, OH, Cl, and CH3 was the Cl, CH3, Br. Now let me put them in the right. Cl, CH3, Br, OH. So CH3, Cl, or Cl, CH3, Br, and OH. Cl, CH3, Br, and OH was the original, that's the original left molecule here. And then the right molecule is Br, OH, and Cl. Br, OH, Cl, and then the CH3. Okay, so here's my two molecules again. Now, group switching requires us to count how many switches it needs to take, how many you need to take to get from left to right, to make one molecule into another. So a couple things about group switching. Number one, you can only use this group switching technique if both molecules are in the same orientation. Okay. And so that means for this one, all the bonds in the plane have to be pointing in the same direction. The dashed wedge has to be in the same direction, and the bold wedge has to be in the same direction. So you can only use group switching when both of the molecules are in the same orientation. If they are not, you cannot use group switching. In that case, you might be relegated to doing RNS. So in this case, I want to convert the left into the right. How many switches is it going to take? remembering that the odd if it takes an odd number of switches, then you have opposite configurations of the chiral carbons, and if it takes an even number of switches, you have the same configuration of the chiral carbons. So if I'm looking at this, the first thing I'm going to do is I'm going to switch the Cl and the Br. So if I switch the Cl and the Br, that's one switch, which then lines up the Br and the Cl. Are the CH3 and the OH lined up? No. So now I'm going to go ahead and switch the OH and the CH3 for my second switch, and now the left is the same as the right. Since it took two switches, that's an even number. That means these two carbons have the same configuration. And if they have the same configuration, then that means in this case that they are the same molecule, they're just not meso. Okay? So that's how we can compare, for instance, two molecules. We can determine R and S, we can do rotations to try and make them one into the other and see if we can line up all four groups or if we can only line up two of the four groups, and then we can also use group switching. Okay.